Hi everybody, this is video 4 of the Simulation and Simio Refresher module, and in this video we'll focus on setting up an experiment and the corresponding experimental responses from our tandem queuing model. So recall from the previous video we had set up our model. We set up what we call our baseline model, and then we ran the model for 100 hours, and then we looked at the results and we were focusing on our queuing metrics. So let's look a little more closely at that. So what I'm going to do is I'm going to filter this. I'm just going to filter it till I can see the components I'm interested in, the average values and the percent values. And you can see that we're reduced we've significantly reduced the number of rows that we see in our pivot grid. And I want to focus on the number in system and the time in system, if we can get there, and the utilization. Let's see, where is utilization here? Scheduled utilization, there we go. Right, and so these are the values that we can compare to our queuing model. So if we go back to our queuing model, let me see if I can shrink that a little bit so that we can get them all on the same page. And we can see that this average 13.651 corresponds to this exact average of 2.26 to the 2.17. And then we have our two utilizations. And for server 1, we said it was 90.5, and the actual value that we expect is 80%. And for the second one, it's 89.6 and it's 90. So these are, again, as I mentioned in the previous video, relatively close, with this one difference here on this utilization. And so if that causes you any concern from a verification standpoint as we go, we can always run longer. So if I were to go in here and say, well, let's run for 500 hours. And then let's just fast forward to the end, and then I can go back and look at my results. Now we can see that this has gotten much closer to what we expect of 80, but now the average number in system has gone from our 13 down to our 10.5. And so we can continue doing this kind of lengthening our run, but the more effective way to do this is to set up an experiment, because what we're looking at here is the results of a single run or single replication of our model. And we don't want to draw too many conclusions. Well, we really shouldn't be drawing any conclusions from a single run of our model. So that's what we're going to focus on in this video, is setting up a model experiment. So let's go back to our facility view and our project home. And to create our experiment, we're going to just click on the new experiment, and there we go. And the parameters of interest for us are the number of replications that we want, the warm-up period, and then the run length. So these are the three things, the three parameters of the experiment that are the fundamental decisions we have to make. So let's just start out with, I'm going to start out with 32. And you might think 32 is an odd number, but as hopefully you remember, Simio runs replications in cores. I happen to be running on an 8-core computer, so it's going to run 8 simultaneously. And so by making this a factor of 8, then I'm going to get the most efficient run. So I'm going to leave this replication run length at 500, but I'm going to set the warm-up for 250. And so remember that what the warm-up does is it hopefully gets you through the transient period, because as we're using our queuing model to do our verification, we're looking for steady state performance. And so as the system starts empty and idle, we need to get through that transient period. And what the warm-up does is it runs the model, and then at the end of the warm-up period, it reinitializes all of the tabulated statistics based on the current state in the system. So it basically just says, starting with the current state at time 250, now start collecting data. And so that hopefully gets us through our transient period. So let's just do that really quickly. So let's just run, and we run our 32 replications. You can see they run fairly quickly. It's a very simple model here. And so once it finishes its run, we're going to look at the pivot grid, just like we did before. For our single run of the model. The only difference in the pivot grid now is that we have multiple replications. So in addition to the average, we have the minimum, the maximum, and the confidence interval half-width. So as we did before, let's filter this down to our statistics of interest. Oops, I just sorted that one. So let me just click on the filter button there, and I want to have the scheduled utilization, number in system, and time in system. And I want the average hours, and then percent. So now you can see that when we've replicated, we're much closer to our expected value of 13, 2.26, while I can pull up the queuing model again so we can get those exact values. So now we're relatively close in all of our computed values, or all of our the recorded values from our model compared to the exact values that we got from our queuing model. And this other piece of information that we have here is the confidence interval half-width. So the confidence interval half-width gives me information about the sampling error associated with the average value here. And so I'm in total control of this half-width. By increasing the number of replications, I can reduce this confidence interval half-width arbitrarily. And so we're going to do that here in just a second. But before we do, I want to add the simulation, the experimental responses, so that we get a quick view of the performance metrics of interest, and we can also use the Smore plots to get a quick visual representation of the simulation results. So we have 4 performance metrics of interest, at least initially. We have the utilization of our 2 servers, the average time in system, which we call W in our queuing model, and the average number in system, which we called L in our queuing model. So we can create experimental responses by using the add response. And so let's do that. Let's just start out with S1 utilization. And as before, we need to have the expression for that utilization. So I'm going to go to S1, which is server 1, hit the period, and we need capacity, and then we have scheduled utilization. So the expression is object instance S1, capacity, scheduled utilization. So for S2, it's going to be similar. S2 utilization, or util, and we'll just use the expression builder again. S2, capacity, scheduled utilization. So there are 2 utilizations, and then we will add our, let's do number in system first, which we called L. So to get the number in system, we need our default entity, population, number in system, average. Exactly what we used when we did the status plot, except this case we're doing as an experimental response, and so what it's going to give us is that value at the end of the run. So the status plot gave it to us as the run was occurring, as the interactive run was occurring. This one is going to give us the value at the end of the replication. Or at the end of all the replications, it's going to give us the average value. And then finally, let's add W. And W is the default entity, population, time in system, average. And we're going to specify the time units here as a time. And since our queuing model is in hours, we will also leave this in hours. So we'll just leave the default units of hours. And so now you can see that we have our 4 responses here. If I want to see those, I first need to reset the model. So let me reset the experiment. And then run, and then you can see what we're getting is that average value. So this average value that we see here is no different than we have the average value in the pivot grid. So if I looked at my pivot grid, once the model finishes here, this 80.442, 90.687, 13.564, and 2.25089 is exactly what I get when I look back over here, because it's the exact same values. The difference is two primary differences. One is that we get those average values here under the scenario. And the second one is that we can also look at the response results in terms of what's called a Smore plot, or Simnio measure of error and risk plot. And so what this plot gives us, and so let's look at the L value, for example, is it gives us a visual representation of the performance metrics. And so let's look at a couple of options here. Since we only have one, at least the way I like to look at it is I like to show the histogram, and then I also like to rotate the plot so I can look at it at the horizontal axis. And what we see is similar to a box plot. And if we hover our mouse right here, you can see that the mean value, the expected value, and then it also gives us the confidence interval. So you can see the confidence range there in the pop-up, and I can also see visually that confidence range or the confidence interval by this beige box. And so I can either get the numerical value or I can get the visual value, visual representation. For the box plot, we also have the median value, and then we have the lower 25th percentile and the upper 75th percentile. And note that this 25 and 75 and also the confidence interval values are specified as properties. So we had talked about the number of replications and the warm-up period, but we can also specify the confidence level and the upper and lower percentile. And so we just use the default values of 95% for the confidence, and then 75 and 25 for our lower and upper regions. And so I also mentioned before that we are in total control of this confidence interval width, and this is really easy to see if you look at the Smore plot. So I'm going to go back to my model, and let's just increase this. Let's say that we run 100 replications, and then I click go, and then I watch that happen as the model runs. But I look at the Smore plot, and you can see as the runs go, and they're going in batches of 8. As I mentioned, I have 8 cores. Is that this value is getting smaller and smaller. This confidence interval on this lower percentile and the confidence interval on the upper percentile are also getting smaller and smaller. And so as we increase the number of replications, those confidence interval half-widths are getting smaller and smaller. And so we can continue until we're satisfied with the amount of sampling error that we get. So as I mentioned before, the confidence interval is a measure of sampling error because we're trying to estimate a population parameter based on a sample. Because the sample's finite, then there's sampling error. I can reduce that sampling error by just making my sample larger. So we see that for L, and we have the same plot for W. So we have the timing system here, and then our 2 utilizations, we can get a view of those. And so when we think about how to set these parameters, as I mentioned before, we have a few parameters that are of interest. One is the number of replications. 2 is the number of the run length. And then 3 is this warm-up period. And so if you want to really be sure, then the thing to do is to make these values bigger or to overestimate these values. So if I went, for example, and said, well, let's warm up for 500 hours and let's run 1,000 hours, then I'm generating more runs. I'm generating more data than I had before. So if I go back and rerun that now, so just reset the values and run, one thing we're going to see is the runs take a little bit longer because I've increased my total run length. I've doubled, in essence, my total run length for each replication. But it still runs relatively quickly. So we're running, we've run 16 out of our 100 already. So let's just watch this run, go back here and watch this run. Let's do it from the, L. For some reason, the numbering system is always the performance metric in queuing models that, at least for me, is the thing that gives me the most information. So we'll just let this run for a little while till we get to 100. See, we're about 52% of the way, 56% of the way, so it shouldn't be too long before we get to that ending value. And so what we're going to see is that the confidence intervals, the beige one here around the mean and the 2 light blue ones around the lower and upper values are going to end up being quite small. And so we're going to then be able to compare that to the value that we know to be true from our queuing model. Okay, so here we are. Again, if we hover, let me bring up this, if we just hover this value, you can see that our mean, the confidence goes from 12.7 to 14.37, and the mean value that we computed is 13.5. Again, we know the exact value is 13, assuming that we did our queuing model correctly and assuming that we did our simulation model correctly. This number, and these 2 numbers are exact. And so if we want to see that, or if we're still not comfortable in the fact that the expected value that we computed is not 13, it's actually 13.5, we have a couple of options. We can run more. So I could go back in and lengthen the run. I could increase the number of replications. So I'm going to do that. I'm going to do both of those. I'm going to pause the video here, and then we'll come back. What I'm going to do is I'm going to say, let's run 200 replications, and let's increase our run length another factor of 2. So let's just make that 2,000 hours. We'll leave the warm-up period at 500 hours. Let me reset and run. And then, as I said, I'm going to pause the video and then come back when this is finished. Okay, so we're back, and you can see that our 200 replications of 2,000 hours have run to completion, and you can see our expected values. And then if we switch over, you can see the Smore plots. And so here's our number in system L value, which we know the true mean is 13. And I can see we're closer, the sample mean, 13.2270, and the confidence interval clearly covers what we know the true mean to be. So we could continue this process if there's still some concern on whether the model's correct, because when we think about what's going on here is that in this case, we know the exact values and we're not getting the exact values, but what we suspect is going on is there's sampling error, because again, the confidence intervals that we have cover those true values. But we could continue this process. So if we were uncomfortable with the width of this confidence interval, which again is an estimate of the sampling error, we can reduce it by simply running more. Do this by increasing the run length, increasing the number of replications, or both. I'm going to leave that to you to experiment with, and you should. If you run this model long enough, if you were to say run for 10,000 hours, you're going to see that this is going to tighten up. The confidence intervals will get very, very small around those exact values that we compute. And that's really the idea of doing verification, or one mechanism for doing verification is to have some expected results and then compare those expected results to the results that you get from the model. And because this model is so simple, we can get those exact values. We can get the exact values to do the verification. So clearly, if what I was after was the expected time in system, or the expected number in system, or utilization, and I met all of the queuing assumptions, I would never use a simulation model, because, as I said, I can compute these values exactly. I don't need to simulate it. But if I want to compute these under different conditions, which is what we'll see in our subsequent models, then simulation is a much easier tool in this case than queuing. But the queuing model is still useful to do this initial verification of our model. Okay, so the last thing I'm going to do, this completes our baseline model. So I'm going to go back here, and I'm just going to change the name of this model. So I'm just going to right click and do rename so that I can call this baseline. And then in subsequent videos, we're going to use this baseline model and then make some modifications where we will no longer have the standard queuing assumptions that we had before.